Okay, so I want to demonstrate this capability called INT, in-band network telemetry here. Essentially, INT is a mechanism to, that allows you to recruit any data packets as probe packets. Right? So imagine that so this end host, suppose end host generated packets going into the network, and the first hop switch can essentially add more data, metadata to this packet. So for example, it can set an INT instruction bit, basically say that, hey, for these packets, the next hop switches, all the subsequent switches, do something for me. Right? That's what INT source does. And then it also adds its own metadata, say switch ID, input port ID, output port ID, queuing latency, arrival timestamp, congestion status, instantaneous queue depth, anything that the switch knows. And then this packet is forwarded to the next hop. The next hop does the same thing. It adds its own stuff, and then it keeps going on this way. And when this packet actually arrives at the last hop or the last hop or the end host networking stack, the INT instruction and the metadata collected can be just stripped off from the original packet because you don't want to disrupt your applications. And then the application receives just the original packet, but you as a network owner can collect this additional metadata per packet. So with this kind of visibility, you can ensure a lot of exciting analysis and debugging scenarios for your network. So we actually use this mechanism INT to realize something called path and latency tracking, PLT. So every single new connection, we detect its path and the hop by hop latency, and hence, of course, unidirectional one-way network latency. And anytime it changes significantly or anytime path changes, we just generate records as well. And this INT source and sync functionality, right now in our implementation, we implement it at the switches, but of course you can implement this functionality at the end host by changing your end host networking stack or by changing your hypervisor as well. Okay, so the particular scenario that I wanted to showcase here is this one. So using Mininet and the behavioral model version 2, the P4 software switch, I actually built this kind of large scale but still representative data center network topology. There's two clusters. So this is one cluster composed of 2 racks at the bottom and 2 cluster level spines. Cluster number 2 here, and then these clusters are interconnected by the data center level spines. Okay, and so any east-west traffic should be locally switched either at the top of rack switch or through this cluster level spine or through this data center level spine. And then only north-south traffic will go through this segment between border router and the data center spine. Right? So this is the typical, closed or leaf spine topology. And then I'm going to actually run a real application here. For example, I'm going to run memcached server here on under this type of rack switch on one end host there, and then I'm going to run my own memcached client, which is actually a performance benchmarking tool commonly used. And then let me show you what happens. So here are the two end hosts. Here I just ran memcached server here as a daemon, and I'm going to run my own memcached client here. Okay. So what this client does is it actually generates some memcached workload using a few connections, and then it plots the job completion time for each test. So right now, each test takes about 500 to 600 milliseconds, and this is just a time series of the job completion time over the past 30 seconds. So it's kind of steady state, and this 500 millisecond job completion time is an expected state when everything works fine, when application, network, or whatever works very fine. Okay. Now let's go to the UI here, which collects all these connection records in real time. You can actually see that it detected 10 connections. Why 10? Because I created 5 sessions, but this is each unidirectional flow is detected as a separate connection. So you see 10 such connections. and then they've been running for this long, and then each of these connections path is actually visualized here. So this is where the client sits. This is rack 1, and this is where the server sits, rack 4. So it goes through this top of rack switch, cluster spine, and then it goes to the data center spine, and then it comes back to the opposite cluster. Right? So this connection view actually plots some switches more than once because we wanted to show that all the flows always run from left to right. Right? So you can see that these connections originating from here go all the way here, and then this is the server traffic from the server down back to the client, and it's going through all these 4 data center spines. So very well expected behavior because you have multipath routing. Now, let's see what happens when I kill one of the links here. For example, this link between C2S1 and C2L2. So the server is this host, but the server still, or the top of rack on top of the server still has one connection to the cluster spine, and then I have only one server and one client. So even if I lose this link, it should have enough redundancy and enough capacity. So the routing, actually I'm running BGP protocol here with Quagga, should discover new path and then just reroute. Right? So let's see whether that actually happens here. So let me just kill that link at the BGP level. Okay, this is not a killing one. Okay, sorry, I'm just having a hard time getting that right command here. Okay, this is the command that I need to run. And you can immediately see that something is changing here in application performance. But as a network owner, you don't necessarily see this view, right? You may see actually something else. So as a network owner, you see a different view here. So some of the connections that used to go through these DC spines and directly to the other cluster now goes through the border routers. And this is very weird because based on my network design and routing policy, any east-west traffic should always go through only the cluster spines and data center spines, and they should never go to the border routers because that segment is protected, and I expected that only north-south traffic will go through this. And therefore, I actually provisioned my network in such a way that I have only enough capacity here to be able to handle only north-south traffic. So I actually provisioned this network with lower link speed here. And that actually causes a lot of congestion here. As you can see, sometimes you can see probably red dots here. And so this is a very bad behavior. And you can also check your connection state here by querying this system. 2.1.1, and for the fast, safe 7-minute get data. And we're using Kafka and Spark to gather these connection level records and then process them. So it's got this kind of records. As you can see, the connections experienced pretty good latency. This is end-to-end latency, and each connection is actually plotted as different colors. But all of a sudden, some connections started to experience very high unidirectional end-to-end latency. And if you choose one of these connections that are, this is, for example, one of the connections that experience these kind of congestions. And then you can see that all of a sudden, these routers here, shown as red dots here, appear on their path. And then they're actually adding a lot of latency. So you can, even if you didn't own the applications, just by looking at these things, as a network owner, you can debug, oh, something is wrong. It's not just the new path, but the new path is severely congested. So I can figure out that some applications are actually suffering, and I can also exactly identify the connections, the applications who are suffering. So that concludes my demo. And let me hand this over to John from Intel. But while he's preparing for that, I can answer some questions. Yes?
I have 2 questions.
Yep.
Since you're adding bytes to the packet and it still remains mid-band, do you see any congestion issues as you have more of these packets being
are you worrying about the increase of the packet size because of padding? Yes, there is some impact to that, but it's, we, especially in large enterprises and data centers, people are not worrying about adding maybe tens of more bytes anymore. We're already doing, VXLAN encapsulation for network virtualization. So adding some number of bytes seems to be okay, and modern device can support, jumbo frames and all those things.
Swiss hour for egress port. It depends on that particular traffic timing. When it comes to hour to second, you might get into some throughput issues because of the extra bytes.
Yeah, you basically have to carry, you're increasing your entire network workload by maybe a few percentage. Yeah, but, sorry? No, we're collecting hop latencies. So we don't need to time synchronize the switches at all. Each switch measures its own in to out latency and then embed that value. So if you sum it up, you have unidirectional latency. Yep. Okay, thanks. Sorry, can I take your question, offhand later on? So.
Yeah, is that a problem? No. Okay. Let me pull this up really quick. This is what I wanted. I don't know why this deck wouldn't come up. All right, so the demo we have here is just, what we did is we started with a standard Linux kernel. And we wanted to see if P4 could be run sort of on a standard Linux kernel that's maybe deployed today. So here are the kind of the components that we took. Is you have some P4 program, maybe it's a vSwitch or a load balancer. We have a P4 front end, which is just our parser that runs through the P4 program. It generates LLVM code. LLVM, if you don't know, is a compiler tool chain. So what we're doing is, from the front end, we generate LLVM IR, and then, which is the intermediate representation used by LLVM. And then we can run the LLVM code through a series of optimization passes using the kind of standard opt tool, which comes with the LLVM package. And then from that, we end up with this p4.ll file at the bottom, which is an optimized LLVM IR code base. From there, we can go to any sort of target that's running in the backend that's supported by LLVM. So you could use x86 or eBPF. In this demo, we actually use eBPF. eBPF is a virtual machine that runs inside Linux. And one of the reasons we were doing this is to try to exercise the Linux eBPF code and show that P4 can be used to represent switching at the edge of the network in software in existing kind of code bases. So we didn't actually have to change Linux at all. We just had to add these tools on top of it to generate code that Linux knew how to interpret. The other piece, since we talked about it, is we generate this CLI that comes with the package. So you write your P4 program, you run it through this tool chain, you get a P4 CLI, you get an eBPF program, you can load that program into the Linux kernel, and then you can interact with it using your CLI toolchain. So let me just show you what that looks like really quick. See if I can jump out of this. There seems to be a fair amount of latency if I jump around. Oh, that was the view I had. Okay. Okay. So first thing I'll show you is since we talked about API generation, of course, I don't have VM on this machine. That's all right. So this is a machine running in my lab back in Oregon. So there's the P4. Let me show you the P4. So I just picked not a completely random, but a P4 file that was relatively simple and easy to explain in a couple minutes that was sitting in our test directory. So here it is. It has a few primitive actions. And actually, this is sort of an older version of the spec, so it might be slightly out of date, unfortunately. But so we have a primitives drop, count, modify, and redirect. So the modify is used to modify packets. Redirect is basically a forward action. And there's my email. That's cool. Sorry about that, guys. Drop is self-explanatory, I hope. So we define all these actions. We come down here. We have some counters. As we talked about, I think Ben was talking about headers. So here's a VLAN. It has PCP, CFI, VID, ether type. Actually, should be careful. These might not all be completely accurate. I've probably just made all these up as I was going. One of the nice things about P4 is if you're self-consistent, it doesn't have to be consistent with anything else, right? So don't use these in your network, I guess. Ether type, desc MAC, source MAC, all that good stuff. Build some headers, a couple tables. So here we go. I got a bunch of tables. And you can see there they all do various things. They read some things and run some actions. They have sizes, all the good stuff that we just saw. There's a parser, and I guess there's a control statement here, which is a fairly simple control statement. Just apply, 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 apply. Cool. From that, and I won't run the tool right now, but we generate this header file. And you can see that this sort of follows that enum pattern. So you have all your actions, and you have this string, which is used for pretty printing when you type things into your CLI, so on and so forth. We do the same thing for each action. See if there's anything else too interesting in here. You can see as you scroll down, this is sort of what we saw in the slides. More IDs. So this is a header enum for Ethernet, ether type, source MAC, desc MAC, and the bit width. So this tells the tool how wide all the fields are and how they're expected to look in the right orders. Things get a little more, this is a pretty simple example because we don't have any variable length stuff. As soon as you start doing variable length, they get a little more complicated, but this is the same general style. And so we end up with this header file like this, all these tables, and a set of tools that we can use with this program. So then, I'll show you the other side. If I can find the right screen. All right, so we can kick off our tool. So this is a part of the tool that sits in the background. As you can see, we supports a bunch of different backends. There you go. There's a few of them. It will launch it on the pipeline here, which is just BPF. And it sits there and it waits for you to load a program, and when you load a program, then we can talk to it. So we'll have to go over here and find the right program. Oh, I used this window. All right, so here we go. So then we can take that P4C. I can just show you what one looks like. So taking that P4 program, we could generate this C code. Sorry, guys. Everyone's talking to me now. And this is eBPF code that can get loaded through LLVM, which has a C to LLVM IR compiler in it. The tool can also generate the LLVM IR directly as well if you don't want to go through C. There's actually some benefits to doing that, such as being able to optimize it, use some of the vectorization instructions in IR. You can imagine doing per CPU stuff and all kinds of crazy things if you get carried away. Okay, so, but for now, we just run our CLang tool, emits it. We can run our LLC, which does the IMARC. So this takes the LLC, generates the .o file, and then we need to load it somewhere in the kernel. And so the kernel has a bunch of hooks you can load these programs into. You can load them on the ingress and egress. You can then actually attach them to sockets if you'd like. At this point, I'm just going to use the ingress hook. In like a real program, you might generate an ingress and an egress hook program for each direction, and you might connect them there. But for right now, I'm going to add a hook in the ingress. I'll then add my program. This is what tells it sorry, that string is, if I find my guy, here he is. So he's listening on 102. You can see he tried a couple other connectors, so I have some other programs running in the background on this system. I connect it to 102. You can see I've got everything in debug mode at the moment, so you get a bunch of dump from the thing listening. It says, hey, a program's connected, it has all these tables. And then we can use our CLI, which is sort of fun. At this point, we can do things like, actually, let me just do like get tables. So this will dump all the tables that we just loaded into the kernel. That came from the auto-generated file. It pinged the program that was loaded, and since they all agree on the types and the values of everything, you can get this sort of info back out. You can do get graph, which shows you, this has a graphical output too, but since we're on a terminal, it gives you the kind of just the layout. This is really simple. A feeds B, B feeds C, C feeds E, and E is terminal. So not a very interesting graph, but you could get a better one if you like. In the interest of time, I'll skip the other things, but you can show the header layout, all that good stuff. This thing's telling me I have 30 seconds. So the next thing is we can set rules. You can do things like source MAC, action redirect. So this rule here is adding a rule to table 2, matching the source MAC, and does an action to redirect. So this is basically forwarding to another port using that MAC address. And just to convince people that it's actually working, you can do ping. Pings that runs here, and then additionally, because I have it running in the background, you can then I have debug mode running. Debug mode running. You can see all the debug output in trace if I get there correctly. I don't know why. Normally it's there. All right, well, I think the important thing is I just want to show the tool runs. You get all the output generated from the file, and the takeaway is that Linux can support most of P4 at the moment in a standard kernel. Thanks, and let's see who's up next. Thanks, guys.
Yeah, it's interesting, all these different mappings from one language or data path environment to another. I think we need the tradition that on the 1st of April we announce some really crazy mapping, but then maybe somebody will actually go and implement it, so we'll see. Okay. Just waiting for a slide to come up here. Okay, so I only have one slide here, basically showing you what is going to come up as the actual demo. So because this is a developer day, we're actually going to expect you to go and implement the use cases and the programs yourself. So I'm going to focus more on the development environment in the demo. We've built an environment where you can edit P4 and C code, and you can also go and debug it. And what's interesting is you can debug at these different languages' own level. So if you want to debug at the P4 level, you can do that, or you can drill down into C level if you have C code embedded in P4. So in order to do that, we take your P4 program, and the P4 language is, of course, standardized at p4.org. We used a compiler to go and transform that to an intermediate representation. So if you're familiar with the P4 compiler, it's got something called HLIR embedded in it. Now that HLIR is actually just objects in memory, Python objects. This IR is a file-based IR. It's using a kind of a YAML syntax, and it's standardized at open source SDN.org's PIF group.
That we compile further down into firmware for the smart NIC. We can take C code and link it together with the transform P4 code. So these primitive actions that we heard about earlier, you can go and implement in C, for example. All of that is then sent down to the smart NIC and runs on there. Being a NIC, it has the network ports, but it also has NetDev or DPDK drivers, and you can use them in the host OS or in the guest OS. So without further ado, we can look at all of these details. The runtime interface we offer has a few options. It's got the file-based rules there that you can see, and these rules are edited in the runtime environment with the IDE allowing you to edit them. But there's also an API generated so that you can have your control plane code call the API to access the runtime that way. So let me bring up the actual demo here. Okay, it doesn't want to turn on the mirroring, so I'll just drag over the window. Or maybe not. Okay, there we go. Okay, so here's a view of the development environment. As you may be familiar with many environments, you can go and create a new project. And one has to go and select a target chip type and say it's a P4 project. Now I can go and open a P4 file, which I've already created. And you'll notice that there's syntax highlighting. Sorry, the font is a bit small there. And if you go and... Shall I try to change the resolution a bit? I think you can't really see what's going on. Okay, I think it's hopefully quick to do. Is that better? Okay. So if one makes a mistake in the editor, you would, as usual, get an error in the integrated development environment. I just need to point it to the root P4 file. That's the root of our project. So if we try and generate with an error inserted, we see the build error as we would expect. But if we go and fix that error, we can see one of the nice things here is that it has a visualization of the program. So I can click on the visualization and it will take me directly to the corresponding source code. This is a very simple example, so there isn't that much to visualize. So you can see already that you're operating at the P4 level while you're editing and while you're building this system. If you now go and run it, it will, I started another copy of the IDE in preparation. You can see it has a rule editor. And the actions you can choose are dependent on the program that you wrote. So for example, the table matches the ingress port, and it has a forward action or a drop action. So you can choose those actions and give the action parameters in the rule editor. This then creates the JSON file that you use during the debugging process. If you look at the actual code, you can see that you can set breakpoints at the P4 source level. So if you, for example, set a breakpoint at parsing, then it will stop if it is detecting that header level. So you can maybe set a breakpoint at IP parsing, and then if there's non-IP traffic, it won't go and hit that breakpoint. You can also put breakpoints at the action or the table constructs. If we look at the display here of a packet, it will show you that a thread that was not processing any traffic only has the standard metadata. But if I go to a thread that actually did process the traffic, we can see that it automatically populated based on the P4 source code, the headers, and these are now valid, to the earlier point that if you declare something, it's not necessarily valid for a given packet, but in this case, that Ethernet header is valid. So there's a number of other features here, like debugging at the table level, the counters that are associated with the tables you can look at. There are also system counters that are just overall counters for understanding what the system overall is doing. So in the interest of time, I'll maybe stop here. I think in the labs this afternoon, you'll have a chance to actually go and use this user interface and play with it yourself. Sorry about the display issues earlier. Thanks.
Okay, thank you.
So moving on. So what we are doing here is like we are using P4 as a high-level DSL to specify how a switch should behave. And so far the discussions have been mostly about P4 as a high-level language for specifying the hardware architecture, but now we are like looking into how we can use the same language to define software switches as well. So there is a compiler that takes P4 and compiles it onto OVS. The compiler generates the necessary parse, match, and action code that is needed to build the final executable. And then there is also a flow rule utility, just like you can think of it as a high-level API for programming the OVS executable. So the code that the repositories that we are using are the P4C behavioral. This is available on P4Lang. We use this to implement our compiler, and then the OVS executable is built using LLVM, which is again a general purpose C compiler for building x86 or whatever the backend is executables. So moving on, I just want to emphasize that this is real. We have code for both OVS and P4C behavioral. So you can go on to GitHub on the P4 vSwitch organization and can download and start using and testing this code. Because this is a demo, so I'll actually jump directly into showing how we can use and run this. So first of all, we have to download the P4C behavioral code in your VM or hypervisor, whatever you're using. And then we have to install this code using the Python setup install script. So once you do that, the HLIR code and the P4C behavioral binaries are all now set up, and the OVS compiler can now call them and use them to build the final executable. So in OVS, again, we download the code, and in order to build it, we have augmented the existing build system of Open vSwitch to now take a P4 program as input, so that once you are compiling, you get the it will now have the necessary match action fields and the tables and the control flow structure in the code itself. So I'll just give you a quick look at how you can build this. So in this code, you can see all this is necessary logic for setting up the environment, building DPDK, because we are using user space version of Open vSwitch. And then at this point, you can see we are specifying the P4 program that we want to use. And we are also specifying where we want to generate the output of the code that I will show later on in the talk. And then we just run the standard make clean and then run it with using J32 just to make sure that it builds quickly. So after setting this script, we can just run this script, and then what this will do is this will first of all build the necessary base system that OVS has. Then it will call the HLIR and the P4C behavioral binaries to generate the C code that is then called by the OVS build system to generate the final executable. So I'll let this finish. So once the code is built, then what you have to do is you have to run the OVS DB server. So again, this part is not something that changes for every P4 program. It's just you can run this as a daemon in a normal Open vSwitch logic, and you don't have to change it again and again. The thing that changes is actually the vSwitch code itself, because now it has the new fields that you want to match on, the actions that you want to use, and so forth. So this is the part that you have to run again. So we just run this. So once the switch is running, then what you can do is you can install the rules. So for now, the utility that we are using is actually an extended version of the OVS utilities that are already there for programming Open vSwitch. So we install the rules. And this time you can see the interesting thing that I want to mention here is the new fields that we are using. It's not the DL dest field that the vanilla OVS has. It's now the exact field that we use or specified in P4, and we are calling the same one here to specify a match or an action. So once the rules are installed, the next thing is I just want to give you a quick view of what is in the what is actually installed in the switch itself, in the running switch. So let me just call the. So here you can see these are the rules that are now installed in the running switch itself. Right now, because there is no traffic traveling, so there are no bytes count, so you cannot see them. But still, the idea there is you are matching on your new fields. Again, because we are doing L2 forwarding, so these fields are known fields like Ethernet, destination, and MAC. But again, the idea is similar. You can have a new field here, and you can match on them. So what we do, in this demo, we have this setup where the PySys is running on a remote server, which is based on Ubuntu, and then we have two other machines that are connecting to it through 3 10-gig interfaces. So right now for this demo, I'll just use one 10-gig interface. So what I'm going to do is I'm going to send traffic from one machine to the other one to see if the traffic is actually flowing using the new executable that we have built. Okay, so what we're using for traffic generation is MoonGen. It's an open source traffic generator based on DPDK. So what we are going to do is like we are just going to generate a simple Ethernet packet, and we are going to see on the other machine that whether we are receiving the packet or not. It's not a fancy thing. It's just like making sure what is built is actually working or not. So you can see we are now receiving traffic on the receiver side as well. And also to make sure that the switch is actually working, it's not like something P2P happening in the back end, I can show you that the counters in the actual switch are actually changing. So you can see the byte counts are actually increasing whenever you do a new, whenever you query the flows themselves. So, so the whole idea there was to just give you a brief idea about how we can compile P4 to OVS and whether it's real or not. So this is sort of like a ground truth for this is actually happening. So in the end, I just want to give a brief overview of what is the P4 to OVS compiler generating. So when I say we compile P4 to OVS, what we are doing is similar to what the Intel guys do in eBPF. We generate a bunch of C code, and then we call that code from inside the modified OVS executable. So here, I just want to give you an idea about like what that code is and what are the different number of files that you're generating and the complexity in terms of the number of files and the lines of code that you have to write if you're doing the modifications directly in the Open vSwitch. So this is just a simple P4 program. We have an Ethernet header, a simple parser, and then a few tables for source MAC, destination MAC, and ingress. Maybe I can try to highlight this. So yeah, so this is just a bunch of code. It's already, so this is the code that is already available on P4 Lang. It's not something new, so we just use that for this purpose. And so once we run the P4C behavioral, which is the P4 to OVS compiler part in our compiler, what it does is it generates a bunch of different files. Like here you can see there are two folders that are generated for the OVS. One is for the match part and the action part. What I mean by match is like whenever you are adding a new field and the functions for modifying those fields, I sort of like considering them as a match part. Like adding a new field is like a match part, and anything associated to that is something that goes into this folder. So for example, you can see we have a flow.h file. So even though the P4, like this L2 switch.p4 program itself was very small, the single flow parser in OVS is like taking so many lines of code. So you can see we start with our state machine with the mini flow extract. We go into the parser Ethernet state, and then we go on to IPv4 and so forth. So similarly, there are a bunch of other like functions that need to be generated, like packet structures, the header structures for all the packets, then how you want to modify them using set field operation and so forth. So this is just for adding a new field and making it available throughout the OVS base system. And then if you want to add like new actions, say, so what I mean by action is something that is more complex in the sense like doing a checksum or doing a hash or something like that, then you have to go and like write those codes separately. Like we generate a field list for this, then we do CRC functions like for adding or removing headers and so forth. So there is a bunch of code that gets generated for when you want to modify OVS by itself. So this is where P4 helps us in as a network programmer specifying something in a more concrete and in a more concrete fashion versus going into different places in the Open vSwitch and then doing these modifications in a very indirect manner. So yeah, so with that, I just want to conclude my talk, and you can download the code at the GitHub organization here, and yeah, that's it. Thanks. Any questions?
We can take one quick question.
Hey, yeah, hi, Bob.
How does the sort of performance and efficiency compare, to compile an L2 switch or switch.p4 to OVS versus using OVS's built-in sort of hand-coded?
Yeah, exactly. So this is something that we are slightly going to mention in the talk that is coming after this, like compiling P4 to OVS. And then tomorrow we are going to go in detail, like what are the optimizations that we did. So there's a SIGCOMM paper coming up where we talk in detail about all those optimizations.
You're giving a demo and talk
Yes,
tomorrow.
tomorrow as well.